Good morning, good afternoon, and good evening, everyone. So today we're going to be continuing our exercises here on minimum and maximum values of basically observing quadric surfaces, right? So here we have a box, and the volume of that box is 5832 cubic centimeters. And we're being asked to find its minimal surface area. So how do we do this? Well, we want to get the surface area of the box, right? So here we want to find the surface area. So how do we find the surface area of a box? This is what a box looks like. And it says here that it has X, Y, Z dimensions. So we can say, okay, this is my X, this is my Y, this is my Z. And so what's the total surface area of our box? We'll call it SA. So the way we can define this is the area of, oops, my drawing's not that good. It's fine. Okay, we'll pretend that is very, very symmetrical. Okay, cool. So we have, when we're talking about the surface area, we're looking at the area of each surface. How many surfaces do we have? We have one, we have two, we have three, we have four, we have five, and we have six, right? So those are our six different surface areas. So we have X times Y, that's the area of one surface, but we have twice of that, right? Because we have another one. So that's XY plus XY. And we can just restate that or simplify that to 2XY. We also have 2XZs, right? This one and this one. Then we also have 2YZs. So we have 2YZ. And so that's the, whoops. So it's 2XZ, 2YZ, right? So that's the total surface area. Now, how do we find its minimal? So to find the minimal surface area, we want to take its derivative and then set it to 0, right? So here we're being asked to find the minimum surface area. And so here we basically just take its derivative and we set it to 0. So 0 is the derivative of my surface area. And we actually do it in terms of X and Y. So we actually take partials here. So we take a partial of my surface area with respect to X. We set that to 0. We also take a partial of my surface area with respect to Y. And then we get something out of that. Oh, I just realized we have to, yeah, because we have three variables here. So that's something I didn't realize. But we have to take into account if they have, because this one has three variables. So we want to make it two variables, right? How do we do that? Mm-hmm. Let me go check. Yeah, because here I tend to forget these. Okay. Hmm. Use the constraint to eliminate one variable. And then we take partial derivatives. Oh, okay, okay, okay. So this is an optimization problem, right? So we actually need two things. We need what we know as a given, but we also need something that we can derive. So we not only need the surface area, but we also need to state the given. And so in this case, that's the volume. And then that's where we can derive some stuff. So my volume, I'll denote it as V. This is just X, Y, Z is equal to that number, 5832. And that's for any optimization problem, right? And then from there, we want to replace Z in terms of XY using our given, right? So our Z here in this case is just 5832 divided by XY because we divide the product XY to both left and right hand sides of our given equation. And then from there, we just replace that to our surface area. So our surface area is now 2xy plus 2xz. So 2x times 5832 over xy. And then we do it again. 2yz. Here we do it again. And then we can simplify some stuff here. We cancel our x. Here we cancel our y. And so we get 2xy plus 5832, and we multiply that by 2. So we get 11664 over y. Then this one's the same thing, but this time it's over z. Or over, my bad. Oh, we have a z here. I almost forgot. We had a z there. So here we actually put a z here. Here we also put a z. This is over x this time, right? Oh no, my bad. Because I already had my, what am I doing? Because I already replaced my z with this value. So there's no, my bad, my bad. So this is supposed to be nothing. And now my eraser is not working. Okay, there. So let me just take out my z. If my OneNote wishes to collaborate with me. Okay, so here I have that. And this is now a function of two variables, right? So what's gonna happen? I'm gonna make this a function of two variables because it is, right? And then from there, I'm gonna take its partial derivatives and find its critical points. And then I solve for x and y. And then I solve for z. So here, that's the idea. So now we want to find critical points. And so we take its partial of that function with respect to x, one with respect to y. So here I'm going to say, okay, this is 2y. This is 0. This is 1 over x, which I believe is x to the -1, -1 over x squared. So I actually have negative this over x squared. And then I'm gonna make this equal to 0. Then my other partial here is when it's with respect to y. So here I treat y as my variable. And so when I take the derivative of each term, I make sure to take the derivative of y and treat it like how I treated x here. And so this is minus. Oh, look at that. The rows have switched. Now this is y squared. This is also equal to 0. And then from there, now I have a system actually, because I have x and y on both sides. And so now I want to find x and y. So I can say, okay, this is 2y equals this. And I can say x squared is equal to this. I could divide it if I wanted to. So 1164 divided by 2 is 5832 over y. This becomes that. And then from there, what's the best way to do this? I think what would be funny is if I take the derivative of x squared. That way it becomes 2x. And then I also take the derivative of the other side. I think that's a smart way to do it. Because I just get 2x instead. But I'm not going to do that because that's too funny. Or actually, wait a minute. Is it 200 IQ play? Should I just do it? Fine, what's the harm? Let me just do it. So we do an implicit differentiation. So this becomes 2x. This one, however, oh, I don't think that works. Yeah, that doesn't work. I don't think so. Because here I'm differentiating with respect to x, this one's with respect to y. So it is going to be different. When I'm doing an implicit differentiation, I have to differentiate both left and right hand sides with the same variable. That way it will convey the same meaning. Here in this case, it doesn't. So what I'm going to do, let me think. Okay, since I don't want to deal with square roots, I'm going to say this becomes y equals 5832 x squared. And so if I want to put a square, I just put square there. And so I'm going to get y squared is just equal to this squared. So 5832 squared. Oh, that's a big, very, very big number. Okay, I'm gonna, should I just let it be like that? Just to make it super simple? Nah, it's okay. And then this is x to the 4th, because I squared my x squared. And then from there, now I go here, and I do the same thing. Actually, I did not realize I could have factored out 2 here. I just realized I could have done that. Let me actually do that, because this number is too big. I'm not comfortable with it. So what I could have done was factor this out. This is actually just y. I divide it by 2. This one is 11664. I divide that by 2 as well. I get 5832. So I get this. And I pretty much get the same thing here. 5832. And then from there, I just do the same thing. So I get y is equal to 5832 over x squared. And then I just plug that in here. So I get, oh, this is actually easy. So I get x minus 5832. I square this thing, so I get 5832 over x squared. I square that thing. And that's equal to 0. And then from there, I actually just get 5 minus 583. Or wait. Let me compute it here in one go. This is 5832 squared. Okay, I got that thing. 3401. 2224 over x to the fourth. And then I actually just multiply this to here. So I get something like 5832 times my x to the fourth over this thing. And then I do this. 5832. I try to simplify. Oh, shoot. So I can't. Huh. What if I just divide it? 0, 1, 2, 2, 2, 4. Then what I do next is I divide it by 5832. And I get 5832. So here I get 1, 5832 multiplied by 1. So I actually just get x to the fourth, 5832. That's what I get. And that's equal to 0. Then I solve for x here. So here, I could just multiply 5832 to all sides. So I could just say 5832x minus x to the fourth is equal to 0, right? Just so that I could cancel out my denominator. And then from there, I could factor out my x. So I get something like x is 5832 minus x third is equal to 0. And I could say here x is either 0. And then I could also say 5832 minus x cubed is also 0. And here, well, this is just x cubed is equal to 5832. And then I do x is equal to 5832 to the power of 1/3. And that gives me 18. So x is just 18. Or x is 0. And so I have two things here. I have either x is 0 or x is 18. Then I plug that back to my y. So if I plug this back into my y, well, you notice here, this is my equation, right? X cannot be 0. That would make y undefined. So this is not mathematically, this is correct, but realistically, it's not. So undefined. So this is not a solution. So we're talking 18 here. And if we do that, well, now I have, what's this? Y is equal to 5832 over 18 squared. 18 squared is 324. 5832 divided by 324 is 18 as well. And so we actually have a solution here, 18, 18. And so those are the, no, that's the critical point. So the critical point is 18, 18. And how do we find our z from there? Well, we just plug it in the volume, right? So from there, now we want to find the volume, or we want to find z. And so that's just, well, our volume, which is 18 times 18 times z is equal to 5, I forgot, 5832. 5832 And here we also get z as 18. And so that means our dimensions of that box in terms of x, y, z is just everything 18. That's my answer. Right? Okay, the easier way of doing this would be just to use that volume. And since we know it's a box, we just treat all of them as one variable. So we say x is equal to y is equal to z. That's one statement that we have. And so we can just say x cubed is equal to 5832. And then we say x is just 18. And so that means y is also 18 and z is also 18. So that's the other way we could have just easily gotten it. But again, what if we were to try different surfaces? So this is just a basic idea. So we also have to find the surface area of, this is for any surface, not just a box. Any quadric 3D surface. So that's why I decided to go the long route. Okay, we have two more. And then we should be good for now. I'm going to end the video once I go through these two examples. So here we're given a cardboard box. And this box doesn't have a lid. Or I should have just done without lid. So W slash, so without lid. So that's our quadric surface. Has volume, has the volume of 2, 3. Then I think it was 3, 2, 8 centimeters squared. Or was it cubed? Oh, shoot, it was cubed because it's a volume, obviously. And then from there, we're being asked to find the dimensions to minimize the amount of cardboard used. And we're going to let x, y, and z be the dimensions of the cardboard box. So here we're being asked to find dimensions of cardboard box. Or I think it was like material. Oh, I mean, find dimensions to minimize. So now how do we do that? Cardboard box used. So here, again, we're going to copy our steps. We're being asked to find that surface area, the total surface area, and the volume that we have, and our given value, which is the volume. And so, okay, how do we do this? We have a box. It is a cardboard box. Oh my goodness. I I don't draw anymore. That's funny. Whoa, okay. And this is empty, right? So this top layer is empty. That means we don't have to take into account that area. And so we're going to say our surface area, if we do let x, y, and z be these things again, we still have two xy's. We still have two yz's. But we only have a single xz. So that's the difference now. And then we say the volume of this cardboard box is this. X, Y, Z is equal to 223,328. See if we get this without looking at any resource yet. And then we're being asked here again, we're going to do the same thing. We're going to replace z in terms of x and y. Because we want a function of two variables. And so I'm going to use my volume formula. So z is just 23,328 xy. And I'm going to plug that to my surface area function. So my surface area is now 2xy plus 2yz. So I have this thing plus xz. So x times this thing again. There we have it. I could simplify, so let me quickly do that. So I'm going to get 2xy plus, I could cancel this. So I get, I think this was, what was this again? 23,328. Multiply that by 2, I don't know what that is. 46656 over x, right? Then here I cancel, in the next term I cancel my x, so I have that same thing, but without the x in the denominator. And then I could even simplify, actually let me do that later. So now I have this. And this is my, or also my function in two variables. Then what's the next thing I want to do? I want to find the critical points. It's the same problem, right? We want to replace z, plug it into the surface area, get a function of two variables, find the critical points. So here we want to find the critical points. And so what are the critical points? We take its partial with respect to x as well as with respect to y. And so here, I treat my x as a variable. So I got 2y plus, or minus actually, minus 46656x squared. And then that's just 0. And I'm going to make it equal to 0. Then here, I have my y. So here I get 2x. This is 0. This is minus 23328. Y squared is also equal to 0. And then from there, I can divide everything by 2. So here I would get y. And then for here, I would actually just get 23328. Right? And then for here, I could take out my x, 23328 divided by 2. I get 11664. So here I'm just simplifying everything, right? Okay, let me adjust a bit. Okay. And then after that, well, now we want to solve the system because we have a system of two variables here, or two equations, I mean. So we have 23328 over x squared. And so here I could plug that in. I would get x minus 11664 over this thing squared. What is that? 23328 squared is, oh my goodness, 544195584. I cannot. That's 544 million. Cool. I divide this by x to the fourth. And I equate that to 0. And then from there, I could simplify this. So this would be So this thing divided by 11664. Okay, so here I would actually get 11664 times x to the fourth over that big number. So here, if I actually just divide both of them by this value, this is 1. This is 46656. So I would actually just get x to the fourth, 46656. And that's good, right? And then from there, I equate it to 0, obviously. I could solve for x. So this would give me 46656x minus x to the fourth is equal to 0, right? I could factor it out and then factor out my x. So I would get x is, I think it's the same thing I did in the previous one. Yeah, it's literally the same thing I did. That's funny. Then I factor it out, I get 46656 minus x cubed equals 0. And then after that, I could just do x is 0, or x is something else. 46656 minus x cubed is equal to 0. So my x is just 46656 to the power of 1 over 3. I get 36. So I get these two things. Now, which one makes sense? If I plug in my 0 here, this is actually undefined. So I can't get y. So this is not possible because it would make that equation undefined. So that's not a solution. This one's possible. So I'm going to plug in my 36 here. I get 36 cubed squared. I almost said cube. So that's, if I plug in my x there, I'm going to get y is 23328 divided by 1296. That's also 18. So those are my, well, that's my critical point there, right there. So my critical point is exactly at 36. Now, how do I find my z? That's the last thing. So to find z, I just plug it back to my volume. So find z. So I plug it back into my volume. So I get I get 36 for my x, 36 for my y. Z is 23328. Right? What would that give me? Z would give me 18. So those are my dimensions. So my dimensions would be x, y, z is 36, 36, 18. Done. Right? Okay, I guess I didn't need the, yeah, I didn't need the, what do you call that? The video. I was gonna log the video. Last one, then we'll call it a day. Volume. So here I'm being asked to find the volume in cubic units of the largest rectangular box in the first octant. So what in the world does that mean? Well, that's an issue. So, okay. Oops. Why did I write it like that? That's so weird. So the first octant of my 3D space. That's interesting. It's asking for the volume of the largest box in the first octant with 3 faces. in the coordinate planes. 1, 2, 3. And one vertex in a particular plane that we cannot visualize. Okay. So with 3 faces in coordinate planes. So I think the best idea, or the best idea to go for here is to draw it out, right? And it also has a vertex. So I didn't know a volume could have a vertex or something like that. I thought it was like only a parabola or something along those lines. Never would have expected it to be a box. Anyway, and there's this one vertex in this plane with equation x plus 2y, is that plus 3z is equal to 9. So here, so again, it's an optimization problem, but now it's asking for a maximum. When we hear the word largest, it usually means maximum. So how do we go about that? That was tricky. So I guess the first thing I'm going to do is draw my 3D space, right? Yeah, let's try this without the help first. And then, okay, I want my volume. And it says that the volume of the largest rectangular box in the first octant, so it's talking about this, the first octant, with 3 faces in coordinate planes. So what are the 3 faces in coordinate places? Coordinate planes. Why are they right places? In coordinate planes. What would that be? What's the first face? That's one. I don't know. I'm gonna write something random. That's the first face. That's the second face. Then that should be the third face. Right? Then that's my rectangle. Now, how do I make, what does it mean to be large? Oh, also, and one vertex in the plane, x plus 2y plus 3z equals 9. Now, I don't know what that looks like in 3D space, but I do know one thing. This has a normal vector of 1, 2, 3. And so what can we say about that? We can say, okay, I go x1, I go y, one vertex. When we mean vertex, oh, vertex. I don't want to assume. I don't know how that vector's pointing. But I feel like it should be something simple. Maybe, I think it's that vector that goes here. I think that's what the vertex is, right? Okay, let me review a bit of high school math. What exactly is a vertex? It's the highest point, top, apex, angular point, polygon, polyhedron. What about in a rectangle? How about that? One of the 4 corners where the sides of the rectangle meet. So it's the edges. Or no, wait. Points where lines or edges intersect to form shapes corners. Oh, so this is a vertex. This is a vertex. This is a vertex, 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 right? So that's a vertex. Why? Because in a rectangle, it's one of the four corners where the sides of a rectangle meet. So a side and a side, they meet, they intersect. And each corner has a vertex. So a rectangle has four of them. But if we take its volume, then we have an 8. Right? Because you just multiply it by 2. And then from there, what can we say? Okay, I'm gonna assume that this vector here, this normal vector, is that's pointing there. So I'm gonna say this is vector n. How do we do that? Yeah, that's the vector pointing there. So here, let me write it like this. Yeah, let me write it like that. Okay, and then after that, what are we trying to find? We're trying to find the volume. What do we need? Based on our previous solving strategies, we can find the surface area and the given volume. So what's the surface area of this rectangle? It has some x, some y. Ooh, that's interesting. So the idea, let me, I hope I'm not getting it wrong. This is not drawn to scale, by the way. But the idea being, if, let me see if I get this. If I do, I'm going to be the happiest man in the world. So, I'm kidding. So this here is 1x, right? That's 1x. This here is twice of y, right? 2 times y. And then going up is 3z. I think that's what it's trying to say. Because how else would we get the volume or the sides or the surface area of this particular rectangle? So we have this. And so what's the volume is just multiplying all of these together, right? The surface area is, yeah, that. But okay, another issue. We don't have a total of anything. We just know this plane. And so that can be our given. So I don't think we need a surface area in this case. We just need something that's given and then something that we need to find based on that given. So what we need is, we don't need the surface area. We just need some given and some unknown. So find given and unknown equations. So what do we need to find? We need to find the volume. The volume is basically V. We just multiply all these. X, 2y, oops. 2y, 3z. That's it, right? We don't have any more info on that. Now we can simplify. We can say this is 6xyz. We could do that. No biggie. And then for the plane, that's what we know. X plus 2y plus 3z is equal to 9. And so we can use this because it's a classic optimization problem. We can replace z. So let's just do that same thing. Let's replace z in terms of x and y. And so how is that going to look like? Let's look at our given. We have 3z is equal to 9 minus x minus 2y. And we divide everything by 3. So z is 3 minus, divide everything by 3. I think this is 1/3 x, or Let me just do x over 3. Let's keep it simplified. And then this is minus 2y over 3. Let's make it into that form. And then from there, now we can plug it into our volume. So our volume is now a function of two variables. And we plug in z there. So we have 6 xy. Oh no, it's not loading. And then my z is, in this case, 3 minus x over 3 minus 2y over 3. Right? Classic optimization problem. And then from there, we just multiply everything. So here we would get something like 18xy minus, this one I believe is 2, x squared y. This one I believe is 6 divided by 3 is 2, or minus 4 xy squared. There we go. Now we have that. What else can we do? We can factor out the 2, but we don't need to as of now. We can factor out an x and y, but we don't need to as of now. So that's our function of two variables. And then from there, again, we find our critical points in terms of x and y. Right? So we find our critical points. Critical points in terms of x and y. So here we would get actually, okay, here we get, wait, what do we get? We get our partial of f with respect to x. So here this would give us 18y minus, this is minus 2y. And then I take the derivative of x squared, so that's minus 4xy. And then this one I just do minus 4y squared. Then I make it 0. And then here we see a lot of that. It's a parabola. However, it's a concave down parabola. So that means there's a maximum that's happening here. So somehow this is making sense. We also take the partial with respect to y. And this will give us, okay, 18x. This will give me minus 2x squared. This will give me minus 8xy. And so again, it's another maximum thing. We make it 0. And then now we can solve for their x and y values. So I can divide everything by 2, right? Let me just put that, let me put like a system here. So if I divide everything by 2, I get 9y minus 2xy minus 2y squared. Then here I do the same thing. I divide everything by 2, I get 9x minus x squared minus 4xy. And these are both equal to 0. Right? And then from there, now this is tricky. Why is it tricky? I have to solve for one of them in terms of the other. Okay, let me isolate my, what's easier? I think I have what's easier to do. I guess I can isolate my x here and plug it into here. Yeah, let's try doing that. So just a little bit of solving here, or algebra, I mean. I get this, right? And then I do, so I try to isolate my x here. Okay. Then I do x's. Done. And then I could simplify, sure. So I get something like 9 over 2y minus y. Because this is 2y squared over 2y. I could cancel these out. This becomes y, this becomes 1. So I get that. And then now what do I do with this thing? I plug it in to this other function or this other equation. So if I plug it in, I get 9 of this thing. It doesn't look easy because I have this squared thing. So that's an issue. Oh, crap. Um, that's hard. Because then I have to expand and everything, right? Find the volume. Yeah, it's just asking me to find the volume. I need to find my critical points though. So that's the, or there could be an easier way based on how I derived it maybe. Because this one already is complicated on its own. So there could have been an easier way, I think. X plus 2y plus 3 is equals 9. Could I have, hmm, or my derivation is just wrong. It's another thing. Yeah, when I see something like this, I would just give up because it looks complicated. I feel like I'm not gonna get anywhere. Yeah, this looks hard. Okay, I'm gonna I'm gonna look at how someone would solve it. Yeah, how would someone solve this thing? So they do a partial. Okay, what? Okay, how do you get xy divided by 3? Think the same thing or something? Okay, so I did get like the whole derivation thing wrong. I thought I was onto something. Okay, this thing's not helpful. I'm just gonna look it up myself. Okay, so what's the idea? How do I go about a problem like this? The box is in the first octant, so meaning my x, y, and z are all positive values. One vertex of that box lies on a plane. So it's on a plane with a given equation. How does that help? The volume of a rectangular box is V equals XYZ. Lagrange multipliers. Can I not do that using calculus? Yeah, the maximum volume, right? Hmm? Okay, they're using Lagrange multipliers. I don't want to do that. I did get it though. So that's okay. Let me ask. Oh, cool. Let me try something else here then. So it's the maximum value of a rectangular box in the first octant. And again, it uses Lagrange multipliers. Or maybe it's just difficult to use. This is the more convenient thing to use. Yeah, I just want to use calculus. Okay, so I eliminate the constraint, so I make z be something. Okay. I substitute it to my volume. Oh, so I did get. It's just that my derivation here is weird. It's just a regular XYZ. So my the way I drew it is kind of wrong. It's just that XYZ. I'm given those two. I didn't need to draw these. My bad. Visualizing it could be good, but in some in some instances, when we're not sure how to visualize it, it could be distracting, right? So that's also something to keep in mind for me as I'm going through this course. Okay, so we have that. We want to replace z in terms of x and y. And so we have this. Let's keep it in this form because I feel like there's a reason why they kept it in this form. Then from there, just erase all of these. I find the critical points, yes. For now, I'm going to erase these. So this is for later. Oops, I think I paused something, did I? Or am I still recording? Okay, I thought I paused something. So from there, I get a function in terms of xy. So I get my volume is xy times 9 minus x minus 2y over 3. So that's my z, right? And then from there, I could simplify it. Or expand it a bit. Doesn't matter. Okay, let me clean it up before I do some computations. This is 3 minus 1/3 x. So I'm gonna leave it in this form because I know I'm gonna be doing some calculus. This is 3xy, x squared y, xy squared. So right, that's the cleanest form I can get it to go. And then from there, I take its partials. So I find critical points. Okay, so same thing again. I find critical points. Here I see, oh, my critical points are, I take my partial derivatives with respect to x and y. I get here 3y minus 1/3. Keep that there. Well, I actually have a 2 here. And then this is minus 2/3. Here I have a minus 2/3 y squared, right? And then I equate that to 0. Okay. Then I have my other one. This is now in terms of y. Let me just double check to see if I got this working. 2x, y is a constant. I leave it. Minus 2 over 3. I leave it. X is, oh, I take the derivative of x. If that's 1, 1 times all of this is just the same thing. Y squared is just a number. I leave it. Okay. Then I do this again, but this time I treat y as the variable and x as the constant. So here I do 3x minus 1/3. X squared is just a number. I leave it. Minus 2/3. X is just a number. I leave it. Here, however, I have 2, y squared. So I make this a 4. Then this is y. And then I also equate that to 0. Then I solve a system here. And I can actually multiply some stuff here to make it easier. So this is 9y minus 2xy minus 2y squared. Right? I could do that. That's equal to 0. What else can I do? I can factor out a y. let me do that in the next one. Here I could multiply a 3. So here I get 9x minus x squared minus 4xy equals 0. Here I could factor out an x. Let me just quickly do all of that. So here I factor out a y. 9 minus 2x minus 2y equals 0. Here I factor out an x. Oops. And so I get 9 minus x minus 4y equals 0. And from there, okay, I realize my y could be a 0, but this whole thing could also be a 0. And so here's when I isolate some stuff. So here when I isolate this, I get that's weird. This is now in linear form. So here I get something like minus or 9 minus 2x over 2 is equal to y. I get that. Then I get 9 over 2 minus x. Is equal to y. Right? So I have these two things. I'm going to choose to plug in this one since this one looks the most kind of optimal. So I'm going to plug this one into my other function here. So I get x, or not x, or yeah, right, x minus 9x minus 4 times this thing. Right? Is equal to 0. And from there, I solve for x. And then once I solve for x, I plug in to my y. Right? Because I have two solutions for y. We're just going to see if both work. So here I have x. This is 9 minus x minus 36 over 2. All right, could have just done 18. Minus 18 plus 4x is equal to 0. And I could have just done 9 minus 8. This is minus 9. Right? 9 minus 18. And then this is 3x. 3x minus 9. There we go. Now I have two things. X could be 0. Or this thing. 3x minus 9. So x equals 3. Could be a 0. And so if I plug in both, and now I have two things here for my x. If I plug in both to get my y, I would probably get something like this is y is either 9/2 or y could also be 9/2 minus 3. 3, that's 2, 6. 9 minus 3, or 9 minus 6 is 3. 3x, right? So those are the two things that y could be. Or y could also be 0. Yeah, there's basically there's a lot of critical values that we can go for, right? So that's interesting. So here I'm actually gonna take out y equals 0 because that gives us 0 volume. And we all know that it's positive. So I'm actually gonna take out this idea. Now I'm left with these two. Okay, we got it. Now we have critical points. We have a couple actually. But yes, we have a couple. So here, oh, I'm also gonna take this one out. My x is 0. because that would lead to a 0x volume. So that doesn't make sense. And so if I plug this in, I also take this out. So I'm actually left with 2. X is 3 and Y is 3 halves. Right? And so if I plug that in, my volume, or to my plane equation rather. If I plug that into my plane equation, I'll get a Z value. Right? So I plug into plane equation to find Z. So this would be, okay, this would be my plane. So that's x plus 2y plus 3z equals 9. This is just going to be my x, so that's 3, plus 2 times, what was this? 3 over 2, plus 3z equals 9. This is 3 plus 3, that's 6. 6 plus 3z equals 9. 9 minus 6 is 3. Z is 1. And so from there, we basically have it. So we want, what was asking? Find the volume. So we have it. Find volume. So now I have my Z. So I just plug everything in. My volume of my rectangle is x times y times z. That's 3 times 3 over 2 times 1. So I get 9 over 2 cubic units. Okay. So that was an interesting problem. Yeah, but it's again an optimization problem. I I tried to think outside of the box. I guess I didn't need to. But yeah, I hope you guys enjoyed and learned a lot, and I'll see you all in the next one.